The first thing we need to talk about before we talk about fluid mechanics is different states of matter, density, and pressure. So in this first figure, we have in figure A, we have a solid, and in B, we have a liquid, and in C, we have a gas. In a solid, you can think of these red dots here in all these figures. These red dots, you can think of them as an atom or a molecule. And so for a solid, you can consider all of the molecules to be connected by a spring. And so they're all rigidly connected together, and each molecule is in order, and they don't change places. Similarly, if I were to push on the outside of one, then the spring would just push back. And so the shape of this solid would not change if I push on it. So the shape of it doesn't change, nor does the volume of it. It won't expand or contract. So in a solid, the shape and the volume remain constant. In a liquid, we don't have these strong connections like we do in a solid, and the molecules are free to move around in relation to each other. So they aren't necessarily kind of always next to the same molecules. So their shape, the shape of it, does not necessarily stay the same. If I take, I have a container full of a liquid here, and I were to pour it out on the floor, then it would take the shape of the floor as opposed to the shape of the container before. So in a liquid, the shape does not remain the same. Volume, however, does still stay constant. The distance between all these molecules does remain the same because they're held together, and so the distance between them stays the same. So volume in a liquid, volume remains the same, but shape does not. And as a side note, as you heat up liquids and solids, the volume does increase a little bit, but for all intents and purposes, we'll say that it doesn't here. It's not very much. And then in a gas, the molecules are much farther apart in a gas than they are in a liquid, and they are free to move around however they want. And so there, if we have a container full of oxygen here, the gas takes up the volume of this container, and it also takes on the shape of the container. However, if we were to open it up, then all the gas would flow out of it, and it would then take on the shape of its surroundings as well as the volume of its surroundings. So a gas does not have a constant volume or a constant shape. Both of these things change. However, the mass remains the same in all of these. All of them have the mass of the gas, even if it takes up a larger space, does not change. It still has the same amount of mass. So with this in mind, now that we have matter that can change its volume, we need to change the way we think about mass. Previously, we looked at mass as a quantitative description of inertia, an object's resistance to change in motion. And now we need to sort of normalize this mass per the space it occupies. So we'll define here, we'll come up with a new definition, and we'll define density. Density, which we use this Greek letter rho, looks like a curvy P. This is defined to be mass per volume. And I do my V's with a line through it there to differentiate between velocity. So the SI units for density are kilogram per cubic meter. Or the US customary units would be slugs per cubic foot. And that's the definition of density. So density is basically just mass normalized per volume. Relatively simple there. So let's say we have here like a pile of feathers and a pile of bricks. Let's say they have the same mass. This feathers and bricks have exactly the same mass. But clearly the volume of the feathers is greater than the volume of the bricks, right? So with a greater volume, since density is mass over volume, we'd say here mass of the feathers divided by volume of the feathers is going to be less than the mass of the bricks divided by volume of the bricks. And so therefore, the density of the feathers are less than the density of the bricks. So, I mean, the feathers are less dense, hence they take up more space to cover the same amount of mass. So the density of the feathers are less than the density of the bricks there. Similarly, we need to kind of change the way we think about forces as well. A force was something that caused acceleration previously, but what if we have matter that changes its shape? It's not just the force that's applied, but it might apply that force over a different area, because the shape can change. So we actually will go through and we'll redefine force kind of normalized per area, and we'll call this pressure. So pressure is, which we use, typically use a lowercase p for. This is defined to be force per unit area. So the SI units for this, SI units of force are newtons, SI units of area are meters squared, so it's newtons per meter squared, which is the same thing as a Pascal, PA. So PA is short for a Pascal, PASCAL. Also, U.S. customary units are pounds per square inch, so our PSI. We also have here PSI is pounds per square inch. That is another unit of pressure. We have other units of pressure we'll discuss later. So pressure is force normalized per area. You can see here in this figure, let's say if you press on an arm, figure A, if you press on an arm with a finger, then a finger is a relatively large area. So I press with some force, and it's a relatively small pressure. If I apply that same force using a needle, the area is much smaller, so hence the pressure is much larger. So we need to talk about, force over area. Definitely plays a role, and that's pressure. Another little note on pressure here is that if we are talking about fluid statics or hydrostatics, this is fluid statics, means that the fluid is not moving, or it's not accelerating, very specifically, not accelerating, just like statics and other, when you refer to statics and other branches of mechanics. So if we're talking about fluid statics, then the fluid is not accelerating, and so the internal forces, the sum of the internal forces are zero, meaning that there's no shear. There's no shear between them. So if you look at the tire over here, then the pressure is these arrows here, and it's just like any other vector, in which the length of the arrow represents its magnitude, and the direction is its direction. You notice that all the pressure is always perpendicular to the surface which it acts on. There are no kind of sideways forces here. There's no shear forces in a static fluid. Okay, so it's always perpendicular. If you look, we have an inset on the right here where you fill up the tire. This is always perpendicular to the walls, so the pressure acts perpendicularly. Same thing with the swimmer over here. The pressure acts on him everywhere perpendicularly. If you notice also with this, the pressure at the bottom of the swimmer is greater than the pressure at the top of the swimmer. This is because pressure increases as we go deeper. And this pressure difference actually is what gives the swimmer his buoyancy, allows him to swim, but we will talk about that in a later video. So for static fluids not moving, not accelerating, we have the fluid, the pressure is perpendicular to the surface which it acts on. Next, let's consider the pressure acting on us right now. So let's say that we are at mean sea level here. So let's say this is mean sea level. And let's say we consider a square, which is 1 square meter large, and we consider all the weight of the air all the way up to the end of the atmosphere above us. Then this weight of all the air above us in this column, in that 1 square meter, the weight of this is 1.01 times 10 to the 5th newtons. So then the pressure acting right here, this pressure would be equal to 1.01 times 10 to the 5th newtons per every square meter. But this Newton per square meter is what we just defined to be a Pascal. So this is 1.01 times 10 to the 5th pascals. Oops. So this pressure is equal to 1.01 times 10 to the 5th pascals. This is what we define to be, if it's at mean sea level, this is what we define to be atmospheric pressure. So we use for the abbreviation here, 1 atmosphere of pressure, so another unit of pressure, is equal to 1.01 times 10 to the 5th pascals. This is the definition of 1 standard atmosphere of pressure. So as you're sitting here, if you're at sea level and you're sitting here watching this video, that is the pressure which you feel on you. 101,000 pascals. Those are 1 atmosphere. That's the pressure you feel, which is about 14.7 pounds per square inch, which is, you know, not a trivial amount, but we're used to it. We've felt that pressure our whole lives. I want to go back up here to this tire. Let's return to this for a second. And let's say we want to find out what the pressure is in this tire. We might do this by putting a pressure gauge on it. So I'll put a little pressure gauge here, and we would place it over the top. We would get pressure in here. This would be the absolute pressure. I'll call it PABS for absolute. It's the absolute pressure, and I'll go into the tire gauge. This is the little stick that comes out that tells us what the pressure is. But let me redraw this over here. We have absolute pressure coming in. And we have this little stick. This is going to have to overcome atmospheric pressure, PATM. So in order for that stick to move out, it has to, overcome the atmospheric pressure that's pushing against it there. So what we actually measure in this tire gauge is something we call, so the tire gauge here measures gauge pressure. So P gauge. So the gauge pressure measures the difference between the absolute, what's coming in, pushing air in, and the atmospheric, which is resisting it. So the gauge pressure is the absolute pressure minus the atmospheric pressure. Or with just a little bit of algebra here, we can say that our absolute pressure is equal to the gauge pressure plus whatever the atmospheric pressure is. If we're at the top of Mauna Kea, if we're at sea level, then the atmospheric pressure, this will just be 1 atmosphere. If we're at the top of Mauna Kea, then this atmospheric pressure would be a little bit less. So, as we will use this result later on as well. But there's our gauge pressure we measure is actually a relative pressure. So you just add whatever the atmospheric pressure, and we will get our absolute.